So to start our discussion of conservation of momentum, let's step back for a second and be very clear about what we're talking about when we talk about a system. And we'll see why this is important in a second. So when we have a system, right, a system is any collection of objects. But again, it's really up to us in terms of how we define a system. So here I can have 1, 2, 3, and let's even add in a fourth object. So here are 4 particles. I can define the system to be sort of whichever subset of these I want. So let's say that I define my system to be just particles 1, 2, and 3. So 1, 2, and 3 are in my system, particle 4 is not. The reason this matters is because there are now 2 different types of forces that I can think about. The first of these are internal forces. Those are forces that one member of the system exerts on another. So let's say that particle 3 happens to pull particle 1 towards itself. That's an internal force. If, on the other hand, particle 4, which is not in the system, also pulls on particle 1, that's an external force. So external forces are forces exerted by something outside the system on a member of the system. And the reason this will become important is that we're interested in finding isolated systems. And isolated systems are one that are free from the influence of external forces. And we'll see why this matters in a moment. So again, to set this up, to set up conservation of momentum, let's talk about the other conservation law that we've been working with for a while now, conservation of energy. So when is it that energy was conserved for a system? Well, if we think about our energy balance equation, so our initial kinetic energy plus the initial potential energy plus the work done by non-conservative forces equals the final kinetic energy plus the final potential energy. Well, again, kinetic plus potential is just another way of saying the mechanical energy of our system. And I can rearrange those energy terms. So basically I end up with final minus initial energy on one side of my equation and the work done by non-conservative forces on the other. And so if I'm interested in energy being conserved, that means I want the same energy at the end that I had at the beginning, which means I want delta E to be 0. So the easiest way to determine when the energy of a system is going to be conserved is it'll be conserved when the work done by non-conservative forces on the system is 0. So just to keep the discussion simple, let's assume that we've got a constant non-conservative force. And so that means I can think about the work done by non-conservative forces as magnitude of the force, magnitude of displacement, cosine the angle between those 2 vectors. So when will the work done by non-conservative forces equal 0? Well, the first option is because there either are no non-conservative forces or there are, but they cancel each other out. So when you add up all the non-conservative forces acting on your system, they cancel. You can have non-conservative forces, but if your object doesn't move and there's no displacement, then again there will be no work by non-conservative forces. And then lastly, you can have non-conservative forces. Your object can have a displacement, but if those 2 vectors are perpendicular to each other, then again there's going to be no work done by non-conservative forces. Energy will always be conserved for an isolated system. And so one of the things to think about is that as we've been working problems so far, and we've said energy wasn't conserved. So let's say the most common example where energy hasn't been conserved is because we've had, let's say, a block sliding down an inclined plane, and we've said that there's friction from the interaction between the block and the plane, and that has caused energy to be lost. Well, what we've done is we've basically defined a system that isn't including all the pieces that are interacting. So that friction force, we're effectively making it be an external force because we haven't defined the incline as part of the system. We've just let the system be the block. And so if we wanted to, what we could do is we could redefine our system to not just be the block, but to be the block plus the incline. And now again, that friction force instead of doing negative work to take energy away from the system, what's actually going to happen is that that friction force will do work, and that work will be converted into what's known as thermal energy. So this is the, if you take your hands and rub them together, your hands warm up, right? That's the friction force. The work you're doing by friction is being converted into thermal energy. Well, this happens when anything slides down across a friction surface. It's much less noticeable, right? You don't notice suddenly this intense heat coming off the surface when a block slides down, but that doesn't mean that it's not there. So if we redefined our system and included what had been an external force and make that internal to the system, so that the interaction between the block and the surface is now internal, I have an isolated system, and energy is always conserved for an isolated system. So this conservation of energy is going to help us think about this new idea, conservation of momentum. And it starts in the same way, that again, if you think about the impulse momentum theorem, right, it's going to basically tell us when momentum for a system is conserved. So the impulse momentum theorem says that the change in momentum is equal to the net impulse exerted on your system. So we know that momentum will be conserved, meaning the final momentum will be equal to the initial momentum, when the net impulse exerted on the system is zero. And so the next question becomes, well, how do you get J net to be zero? And so again, let's just assume for ease of conversation that we have a constant net force. Well, from looking at that equation in terms of how we define the impulse, right? So the net impulse is going to be the net force times some delta t. And again, if we're interested in thinking about how something's conserved, that means, does it stay constant in time? I have to have a delta t that's not zero, right? So if I have a delta t that's zero, that means I only have one instant in time, and there's no point in talking about conservation. So to talk about conservation, I need a different point in time. I need to be able to talk about a final point and an initial point, which means delta t can't be zero, but I also know that it has to be positive. Which means that if the net impulse is going to be zero, the only way I can do that is for the net force to be zero. So the net impulse is going to be zero when the net force equals zero. So how do you let the net force equal zero? Well, again, from what we were talking about initially about systems, I can break this up into two pieces. I can think about the net force as being add up all the internal forces plus add up all the external forces. And the nice thing about when you add up all the internal forces is that Newton's third law comes into play. So Newton's third law again tells us that for every force, there's a second force, right? For each action, there's an equal and opposite reaction that has the same magnitude, points in the opposite direction. So when you add your Newton's third law pairs up, they always cancel out. So the net internal force acting on your system is always zero thanks to Newton's third law. So your net force, the net force total, the total net force, is really just going to be equal to the net external force. And so the momentum of your system is going to be conserved when the vector sum of all the external forces acting on the system is zero. So these are the types of situations that we're going to look for to identify when we can say that momentum is being conserved. All right. Now again, if I have an isolated system, that means that there are no external forces. So momentum is always conserved for an isolated system. So we're going to look for situations where we can recognize that we have an isolated system, and in large part that's determined by what are you picking your system to be. All right, so let's talk about a couple of examples. So let's say we've got two blocks. So block 1 with mass m1, block 2 with mass m2. And we're going to slide m1 across to m2. But here's what we're going to do. Let's bolt m2 down so that even when these two blocks collide, it can't move. So if I think about the free body diagrams, I've got the free body diagram for mass 1 over here on the left. I'm going to treat this surface as frictionless, so I only have to worry about a normal that points up and a weight force that points down. Again, mass 2 is just sitting there, so same thing, it's got a normal pointing up and a weight force that points down, and those things are going to cancel out. I'm only going to be worried about block 1 after whatever's propelling it has stopped acting on it. So again, it's just moving, it's going to slide at some constant speed, and so it slides to the right and ends up coming into contact with block 2. And so when they're in contact, well, now I've got additional forces. So I've still got my normal and my weights for each block. But now there are these two applied forces where block 1 is pushing block 2 to the right and block 2 is pushing block 1 back to the left, and those are internal if I want to talk about my 2-block system. Equal in magnitude, opposite in direction, add them together, I'm always going to get 0. The interesting thing here is if I'm saying that block 2 is bolted down, then there has to be this other force basically that comes from that bolt that's holding block 2 in place that keeps block 2 where it is. So when they're in contact, I have these sort of 3 additional forces. 2 of them are internal, but one of them is this external force, the applied force on block 2 from the bolt. Well, mass 2 just stays there. Block 1 bounces back. Right? So again, once they separate and mass 1 starts sliding back to the left, again, I'm back to the same situation where I just have the normals and weights acting on these forces, and those forces cancel out. So when we think about what's going on through this entire process, sliding over, colliding, sliding back, I have multiple external forces. I have normals from the surface, I have weights from the interaction with the earth, and I have this force from the bolt. The normals and weights cancel out. The force from the bolt does not. So what that means is I have an external force acting on my system, which means that momentum is not conserved for this 2-block system. So I have a net external force, so momentum is not conserved. If I take the same situation, and this time just don't bolt block 2 down. So again, block 1 is going to slide over, they're going to interact, and now they're both going to slide away from that collision. So block 1 will slide back to the left, block 2 will start sliding over to the right. And again, here what you see is, same thing's true about the external forces. I have external forces of normals and weights, but those cancel out. The only other forces acting on my system are these internal forces where the 2 blocks push on each other in the instant that they're colliding, and because those are internal forces, they cancel out. So here's a situation where the net external force acting on my system is 0. Because that's true, momentum is conserved in this situation. So the previous example where I bolted block 2 down, we couldn't use conservation of momentum for our system. Here, on the other hand, we can. So because block 2 is also free to slide, that means there are no net external forces acting on the system, and so momentum is going to be conserved for my 2 blocks. Let's change it up a little bit. So here's 2 blocks moving in different directions. So instead of being 1-dimensional, this is now 2-dimensional. And just to be clear, I'm looking down on this from above. So this is sort of a bird's eye view. But I'm going to do the same thing. I'm going to let the blocks slide towards each other. They're going to collide, and then they're going to bounce away. Right? So a couple things. One is there are external forces acting on my blocks, but just like before, they cancel out. So both blocks have mass. So both blocks feel a weight force pulling them down. They're sliding across some frictionless surface. So there's going to be normal forces, not friction forces, and those normal forces are going to cancel out the weights, and so the net external force from the normal and the weight, those are going to cancel out. The only other forces are the 2 applied forces where the 2 blocks push on each other once they're in contact. And again, those are internal. So those internal forces, Newton's third law tells me, will always cancel out. So here's a situation where, once again, momentum is conserved for my system. So what we're going to do is we're going to look for situations like this where momentum is conserved. So the sort of right up at the top is telling us what the rule is that we're looking for. So momentum is conserved when the net external impulse exerted on the system is zero. So that's what we're going to look for, is situations where the net external impulse exerted on the system is zero, so we can use conservation of momentum.